In this section, we're going to look at how to perform another kind of hypothesis test that uses a chi-squared distribution called a goodness of fit test. In this kind of test, we look at whether the sample data, the observed sample data, we test whether the observed sample data fits an expected discrete distribution. The test statistic that we calculate for a goodness of fit test it's a chi-square distribution, so we're calculating chi-square. And we look at each observed value, subtract what we would expect the value to be for that category. We square it, and then we divide by the expected value. And we add that up for each different category. Okay, so here O are our observed values. This is from our sample data. And the E in the equation are our expected values. And these are the expected values from theory. These is what we would expect from theory. So for example, let's get an example to kind of make this make a little more sense. Say you have a six-sided die. Okay, now theoretically, if this is a fair die, what would we expect? Well, there are 6 categories, right? There are 6 categories, and we would 1, 2, 3, 4, 5, 6. There are 6 ways that we can roll this die. Those are our 6 categories. And we would expect each category to happen the same number of times, right? We expect to roll a 2 just as many times as we roll a 6, okay? But when we actually roll the die, if we do this many times, we may observe a different number. Maybe we roll the 6 a lot more times than any other number, okay? What we can test is, does what we observe match what we would expect? In this case, in the case of a die, maybe if we roll a lot more 6s than we do any other number, maybe that would suggest that our die isn't actually fair, that we're not getting the same amount for every number. Maybe it's a weighted die, and so it actually does come up 6 more often, and it's not a fair die. So this helps us to understand if what we're observing is close enough to what we expect that we say, yeah, that looks to be about right. Or maybe what we're observing, the phenomena we're observing, the different amounts for each category we're observing, maybe it doesn't jive with what we expect, and the distributions are different. We're checking how good what we observe fits what we would expect. Okay? Now, for this goodness of fit test does have a degrees of freedom. It's a chi-square distribution, so it has a degrees of freedom equal to k minus 1. This degrees of freedom is a little different than what we've used to calculate degrees of freedom in the past. In this case, k is the number of categories. In the distribution. So if you're rolling a 6-sided die, then you have 6 categories, right? 1, 2, 3, 4, 5, 6. So your degrees of freedom would be 5. Okay? Generally, the hypotheses for a goodness of fit test are, the null hypothesis is the actual population fits the expected distribution, and the alternative hypothesis is the actual population does not fit the expected distribution. Okay, these hypotheses, when you actually go out about writing them out, they should be written out in sentences. Whenever we've written hypotheses up to this point, we've written them in mathematical notation. But in this case, there isn't a simple mathematical way to express these hypotheses that is easy to interpret. So we write these in sentence form, but we do make sure we write it in terms of the problem. So these are kind of the abstract general hypotheses. Whatever your goodness of fit test is, you want to make sure you express it in the context of the actual problem. In the case of rolling a six-sided die, our null hypothesis would be that the actual die rolls do fit the expected distribution, which is that all six sides and come up the same number of times, right? The same probability of happening. Or another way to say that is that the die is fair. Okay. The alternative hypothesis would be some of those sides come up more often than others, or the die is not fair. So you'd want to make sure you express those hypotheses in terms of your problem. Okay. So for a goodness of fit test to be valid, the expected value for each category needs to be at least 5. So that tells you what kind of sample size you need. Okay. That's dependent on what you expect. Okay, so maybe you expect, well, for a six-sided die, we would expect each side to come up 1/6 of the time. Now 1/6 is 0.1666. Okay, so you would need to make sure, however number of times you roll that die, that the actual expected number of times, this is the fraction or percent, but the number of times you have at least 5 for each of those categories, okay, in order for this to work. As with any hypothesis test, the steps are the same. One, state the null and alternative hypotheses. Two, assuming the null hypothesis is true, identify the sampling distribution. Three, once you have that sampling distribution, find the p-value. And 4, once you've calculated the p-value, you can compare it to your level of significance and draw a conclusion. Whether or not you reject the null hypothesis and accept the alternative hypothesis.